Swayam Prabha. Digital India. Educated India.
Okay, so last time we wrote out this theorem, which is let G hat be obtained from G by the elimination of a weakly dominated. So, let G hat be obtained from G by the elimination of a weakly dominated strategy S hat J for a player J. Okay. Then every equilibrium of G hat is an equilibrium of G. Okay. So, recall what the setting was. We had G, which was a game comprising of n players. These were the strategy sets and these were their utilities, right. This is when I put these curly brackets around the SIs means that I am looking at S1 to LSN. Similarly, curly brackets around UI is U1 to UN, right. So, this was your game G, and then we considered another game G hat, which is formed from the same set of players and these strategy sets S hat I and the same utilities UI. And what was the connection between S hat and S hat I? So, S hat I was actually equal to Si for all I except for a specific player J, and for player J it was equal to Sj minus X hat J. I think I have changed my notations. This was, I used the notation X hat J. Yeah. Okay. So, this is for I equal to J. Right. So, in other words, all other players' strategy sets were held the same. It was player J's strategy set that we changed, and how did we change it? We removed one particular strategy X hat J from this. And what was special about X hat J? X hat J was, so X hat J is a weakly dominated strategy. And what does the theorem say? The theorem basically says that every equilibrium of G hat is an equilibrium of G, which means that you look at the smaller game, the reduced game that is formed from after elimination, then all equilibria that are there of this game are also equilibria of the original game. And we summarize this by saying that that essentially if you eliminate weakly dominated strategies, no new equilibria get created. Okay. So, if you eliminate weakly dominated strategies, then no new equilibria get created. Okay. So, now let us see. So, this only says that no new equilibria get created. All the equilibrium of your of G hat were already present in G, but you could have potentially lost equilibria, right. So, which now when you are losing equilibria, it means that there is some possible strategic outcome of the game which has been eliminated because you decided to ignore a particular strategy for a particular player, right, or you do not ignore, I would say overlook a particular strategy for a particular player, right. So, now question is when can we say that even that no equilibria are lost as well? So, no new equilibria are created, but can we ensure that no equilibria are lost in this process? So, that is essentially the main thing that we are building towards. Theorem: if x hat j, if the above x hat j is strictly dominated, okay, then the set of equilibria of G is equal to the set of equilibria of G hat. Okay. So, this is what we wanted to, this is the main result of this particular exercise, that if you eliminate a strictly dominated strategy for any player, then the smaller game will have the same set of equilibria as the original game. So, no new equilibria are formed and no equilibria of the original game are lost in the process. Okay. So, let us prove this. So, as far as proving this is concerned, we already know that no new equilibria are created. So, it suffices to show that no equilibria are lost. Okay. So, it suffices to show that if x star is an equilibrium of which one? Of G, the original one, then x star. Now, I want to show that it is an equilibrium of G hat, but remember we also showed another small lemma which said that if you have a big game and I consider a smaller game, and if the equilibrium of the bigger game is present in the smaller game, then it is necessarily an equilibrium of the smaller game, right. So, it suffices to show that if x star is an equilibrium of G, then x star just has to be present in G hat, right. Then that is enough, then it follows from there that x star is an equilibrium of G hat. Okay, then x star is a strategy profile in G hat. Okay. So, in other words, what do we need to argue? That we need to argue that if x star is an equilibrium and x hat j is the strategy that you eliminated, okay, then the eliminated strategy could not have been part of any equilibrium, right. If that can be argued, then you are done, because then you are sure that the equilibrium is present even after elimination, right. So, which implies that it suffices to show that is not an eliminated strategy. So, what strategy profiles get eliminated as a result of elimination of x hat j? Now, x hat j is a strategy of player j, right. So, x hat j gets eliminated for that player, but strategy profiles, that means for n players, what gets eliminated? Yeah, x hat j comma x minus j for any x minus j, all other combinations, the others can play whatever they want, all of that gets eliminated, right. So, when you are removing that particular row for that player, every combination with every column or however you want to think of it, all of that gets eliminated. Okay. Now let Tj be a strategy strictly dominates x hat j. Okay. What does this mean? That means regardless of what the others play, Tj is better for player j than x hat j. Okay. So, that means if I look at uj of tj comma x minus j, this is strictly better than uj of x hat j comma x minus j, and this is true for all x minus j in S minus j. So, now what do I do here? I just put in, now this has to be true for every x minus j. So, I can put in my favorite x minus j, and in this case the choice is natural. I will just put x minus j as x minus j star, the equilibrium strategy, okay, the part of the profile from the equilibrium. So, put x minus j as x minus j star, then that gives you that uj of tj comma x minus j star is strictly less than uj of x hat j x minus j star. Alright. Let tj equal to, no, we cannot take tj equal to xj star, because x star is an equilibrium and tj is just a strategy that we know it dominates x hat j. Okay. So, we have taken that x star is an equilibrium of g, right. So, and tj, where is tj? Again, remember, tj is a strategy for in the original game, because it was dominated x hat j from that original game, right. So, now x star is being an equilibrium, since x star is an equilibrium, of is a Nash equilibrium of g, implies what? uj of x star j comma x minus j star is less than equal to uj of tj comma x minus j star, right. And this in turn is, we know that this in turn is, from here we know that this is actually less than equal to uj of x hat j comma x minus j star. Now, what does this mean? So, we now have that the left hand side here is strictly less than the right hand side. What is the meaning of that? This means that basically this x, see what is common here, the x star minus j is here, x minus j star is here as well. So, the inequality is because of this one here. We are still looking at uj, the inequality is because of this x star j and x hat j. It means that these two could not have been equal, because if they were equal, then you would have got could not have gotten a strict inequality here, okay, which means that x star j is not equal to x hat j. So, which means x star j is not equal to x hat j, which means what? Which means actually x star is present in the, as a strategy, as a profile in G hat, because x star j is not x hat j, it is not the eliminated one. So, it is definitely present in the game that you get after elimination, right. So, consequently you get, we have that the set of equilibria remain of G is equal to the set of equilibria of G hat. So, what this has told us is that now that the elimination of strictly dominated strategies is with there is no punishment for that. There is nothing you lose. You don't create fictitious new equilibria, nor do you lose any equilibria as a result of this. Is this clear? Okay. So, this basically justifies for us the whole process of iteratively eliminating strictly dominated strategies. Exactly the thing that we use to solve the game in our previous class. This justifies it, that essentially after doing this elimination, when you are left with only one particular strategy, that necessarily has to be the Nash equilibrium of the original game, right. So, actually let us just write this down formally. So, if the corollary, if the process of elimination of strictly dominated strategies results in single strategy profile X star, then X star is a Nash equilibrium of the original game. So, if you I should have used the word iterated elimination, that's implicit here, that if you keep doing this elimination again and again and you are left with a single strategy at the end, then that has to be a Nash equilibrium of the original game. Why is that the case? Because we just saw that every time you eliminate, you are neither losing equilibria nor creating equilibria, and this happens at every step, right. And so, finally, if you are left with just one single strategy profile, right, one strategy for each player, then it has to be that itself, that particular one that was left is necessarily the Nash equilibrium of the immediate previous game, and also of all the previous predecessors of that, right. In short, the original game that you started with. Yes. Yeah. So I will tell. So, if this happens, then it is a Nash equilibrium of the original game. So, this automatically guarantees also that if you end up with 1, then this is also a proof of existence. That is definitely a Nash equilibrium of the original game, right, because when you are left with just one strategy, one strategy profile, you have a trivial game, and that one point then is the Nash equilibrium of that G hat of the reduced game that you have found, and that is by the theorem is equal to the Nash equilibrium of G. Yes. So, that is what I just, I can show you examples where I will come to that. So, strictness is required. If you eliminate weakly dominated strategies, this result is not true anymore. Okay, you will lose equilibria in the process. Yeah. So, if you end up with one, it is necessarily an equilibrium. Then it's not. Then the statement is not true anymore. Then it is not true that. No, it is a Nash equilibrium of the original game. Okay, but it is all equilibria are not retained. So So there is in fact a stronger version of this. Now, since Shashank has brought this up, let me mention this. So, can I strengthen this by saying something more? Is a unique Nash equilibrium, right? Is the unique is rather than is the unique Nash equilibrium of the original game. Okay. Yeah. So, if after elimination of weakly dominated strategies, if you are left with a single one, then that is necessarily a Nash equilibrium of the original game. Correct. That much holds, but that it is the only Nash equilibrium is not true anymore. Okay. All right. So, it is the so when you are left with a single profile, you have effectively then by this process discovered the Nash equilibrium of the game. Okay. Now, another corollary of this is actually which is implicit in the way I have stated this theorem. See, if it so happens that you are getting eventually to one strategy profile, and that is the unique, that then turns out to be the unique Nash equilibrium of the original game. Now, suppose you eliminated strategies in a different order, okay, and then ended up again at this X star. right? What would that, that would again tell you that it is the Nash equilibrium, it is actually the unique Nash equilibrium of the original game. What this means is essentially if you are ending up at a unique strategy profile, then the order of elimination does not matter, okay? Because even if you, in fact, forget the ending up with a unique strategy, forget about ending up with a unique strategy profile. The very fact that you neither lose equilibria nor gain equilibria means that you can eliminate in any order. The smaller game will always have the same set of equilibria as the original game, okay? Now, the order, this invariance with the order of elimination is again not true for weakly dominated strategies. Once you have, if you are eliminating weakly dominated strategies, the equilibria that you end up with, right, because you potentially lose some equilibria, the equilibria that you end up with is sensitive to the order in which you have eliminated, okay. So, let us actually do one example. Yes, but they would all have the same set of equilibria as the original one. Yeah. So, I have another example. So, okay. So, layer 2, layer 1, top, middle, bottom. So, okay. So, player 1 has, so this is the game. Player 1 has 3 strategies, top, middle and bottom. Player 2 has 3 strategies, left, center and right. Okay, and the payoffs are these: 1, 2, 2, 3, 0, 3, 2, 2, 2, 1, 3, 2, 2, 1, 0, 0, 1, 0. And again both players are maximizing. Yeah, so there are several options. So there are strategies here in this game that are weakly dominating other strategies. Okay, so and the point I want to make is that actually the order in which you eliminate will matter. Okay, so let's go through one or two different orders. Okay, so first observe. Let's take this. So T is actually weakly dominated by M, right? So I'll just write it like this. T is weakly dominated by M for player 1. Is that clear? Why? Because you're comparing 2 strictly greater than 1, 2 equal to 2, 3 strictly greater than 0. Okay, so T is weakly dominated by M. So, but there is weak dominance. So, because in this case you get the T and M give you the same payoff. Okay, okay. So T weakly dominates M. Now, so suppose I did eliminate T. Okay, suppose I did eliminate T. Then in that case, what would I be left with? I would be left with this smaller box here, this one. Okay, so now in this, anything dominates anything else? Yeah, R actually dominates L, again weakly. 2 equals to, sorry, L dominates R, sorry, my mistake. 2 equals 2 and 1 is greater than 0. So L dominates R. Okay, so L dominates R. I can remove, suppose I remove R here. Now I am left with this smaller box here. Now M weakly dominates B. So you can again remove this. Okay, and then C is dominated by L, and so you are left with an equilibrium which is followed by R dominated by L, followed by B dominated by M, followed by C which is dominated by L, and that leaves us with the equilibrium ML. Okay. So, ML is a Nash equilibrium of the original game. That came about from this order. Now, let us see if we can go through another order. So, now let us suppose we take the let us take another order. Let us take the order B is actually dominated by M, right. So, I can eliminate B, so B is dominated by M. So, get rid of B first. Okay, I am not going to keep making marks now. So, let's remove, yeah, B is removed. So, you are left with just the upper box. Okay. Now, in this, anything dominates anything else? R dominates C. Let us see. R dominates C. Okay. Let's see what happens. R dominates C. So, C less than equal to R. Okay. R dominates C. So, I have removed, you can remove C then, and you are left with then Tm and L and R. Okay. R actually then dominates L. Okay. So, then L is gone. So, actually R dominates both in this case, R dominates C as well as L, right. After having removed B, R dominates both C and L, right. So, you can get rid of both. So, L, okay. So, L and C are both been removed, and now you can you have to just compare T and M in column R. So, then obviously T is worse than M, and you are left with, so you can remove that, gives you then that MR is a Nash equilibrium. Okay. So, you can see here what happened was when we eliminated L, actually the previous Nash equilibrium, which was ML, the previous means the one from the earlier order of elimination, that Nash equilibrium is now got eliminated when you eliminated L, whereas and you are left with MR as a Nash equilibrium. Is it clear? So, what does this mean? Essentially, it means that the reason this has happened is because you are eliminating weakly dominated strategies. There are these ties here, right. So, if you take ML and MR, for example, for player 2, they both give payoff 2, right. But you said that R dominates L and you removed L. But actually, it was strictly dominating only when player 1 was playing T. When player 1 was playing M, they were equal, and he eventually ended up playing M in the equilibrium, and that is why you lost out on one equilibrium here. Is fine? Okay. So, in other words, the set of equilibria the set of equilibria of the reduced game obtained by elimination of weakly dominated strategies is dependent on the order of elimination. Does the remainder set of profiles? Yes, it could change based on the order, because you may, yeah, you that could happen. But of course, by elimination of strictly dominated strategies, I mean you follow the same process. You eliminate strictly dominated strategies. Of course, if you eliminate the exact same strategies, regardless of the order, you will get the same profile. But if you are so in other words, you eliminate strictly dominated strategies, but you eliminate them in any particular order, and therefore you are not eliminating the same set. Okay, then you will you could get yeah, could be. I am not sure, but I think one can construct an example where you eliminate something prematurely. That could happen, I think. Yeah. Yeah. So, I mean, what a player, we are not analyzing this as players, right. So, we have, as observers of the game, we have eliminated this on behalf of the players. Okay. Yeah. So, all of these are Nash equilibria. There are actually more. You can play around with this game a little bit more. You will see there are more Nash equilibria also. You can come up with other orders of elimination. And so, all of them are Nash equilibria. It is our effort at trying to arrive at one of them by elimination, which is the problem. So, you basically, we did not have as much justification to eliminate weakly dominated strategies, and as a result we have not properly analyzed the game. That is what the conclusion is. Yeah, no, not at all. So, if you have a unique Nash equilibrium, the question is if there is a unique Nash equilibrium, can you necessarily find it by elimination of dominated strategies? No. So, you will in general end up with a game, you will often have a game where there is in fact generically you will have a game that has no dominated strategies, but does have a Nash equilibrium. Some dominating strategies, but a Nash equilibrium does not exist, yes. Yeah, that is possible. Okay. So, what this has basically done is, now it has helped us in some cases in certain types of problems wherever this process actually converges to eventually one unique strategy profile. In that case, we have basically through a logical elimination solved for the solution of the game, and it turns out that actually coincides with the Nash equilibrium itself. Okay. So, this way of solving a game, like a puzzle, trying to say, okay, this would happen, then okay, then that would happen, and so on and so forth, almost trying to like a logical puzzle. This way you can do in up to this point, when the game has the property that it ends up eventually this process of eliminating strictly dominant strategies ends you with one strategy profile. Okay. Now, in general, what you would be left with is a set of is basically a reduced game from which you have removed all these dominated strategies, and but that's it. You cannot analyze that any further with this logic. Okay. And that is where you need a leap of logic, which is what the Nash equilibrium does. That it tries to then reason about, okay, what are the communication requirements in the game, and so on and so forth. Okay. So, you go into that, you need to get into that whole line of thinking once you have done this kind of basic elimination. Okay. All right. Okay.